Hi everyone and welcome. So today we are going to discuss solution near singular points for ordinary differential equation of this kind that you can see over here. And we will only develop the theory in this video and we will see some examples on the later videos. So let's start. So this is the kind of equation that we will be dealing with, and let's say the point we are interested in, that is the solution reference point is t equals to 0. So let's say the point of interest is t equals to 0, and now what we want to do is that in this equation we want to multiply with t squared. So if you multiply with t squared, we will have t squared y double prime plus t squared q. I'm not writing the t explicitly now. And finally t squared r by p y equals to 0. Now, by definition, the functions t, q divided by p and t squared r divided by p are analytic at t equals to 0. So this might feel a bit odd, because why am I saying that they are analytic, right? So one rationale is that if your p has a singularity that is at 0, that means at that point it's undefined, when you multiply with t squared, that singularity gets vanished. So that's one of the rationale that you can accept. So what one can do right now is that using this fact that t squared, that is this thing, you can decompose this thing as t times tq by p, and this guy over here is analytic at t equals to 0, because I am assuming that p itself has a singular point at t equals to 0. So that's why when you consider this guy, it's also analytic at t equals to 0. Fine. So since p has a singular point at 0, multiplying the ratios, the fractions of q and p and r and p with t squared gets rid of the singular point. So now what you can do is that you can use this. Obviously this is a function of t, so you can expand this as a power series near 0, and let's say the series looks like this: alpha 0, alpha 1 t, alpha 2 t squared, and so on. Similarly t square, oh yes, and there you can enclose this whole thing with a bracket to just to make sure that you don't confuse with this t multiplying with this guy over here. So yeah, now also t square p, sorry, not p, r and p, this function is also analytic at t equals to 0. And let's say I'm writing another power series around t is equals to 0, and I'm naming the coefficients as beta 0, beta 1 t, beta 2 t squared, and so on, right? And now what we want to do, we want to replace them in the equation. That is the equation over here. So let's replace them, and this will be just t squared y double prime plus t, because we only expanded one t and there was another t over here. If you just see this equation, that there was a t squared, but one of the t is going inside this expansion, so another t is left. So yeah, alpha 1, alpha 0, alpha 1 t, alpha 2 t squared, there is a y prime, and finally you can write this beta 0, beta 1 t plus y equals to 0, like this, right? Now what we want to do right now is that we want to apply a solution of the form that is known as a Cauchy-Euler form. So what is a Cauchy-Euler form? So we want to apply, so let me use another color, we want to apply or try, because this is a trial and we want to see whether our logics will work or not. So we want to apply Cauchy-Euler form of solutions. And a Cauchy-Euler form of series solution will look like this. Y of t will be t to the power r, where r is some number, and there is a power series like a0, a1t, a2t squared, and so on. Okay, so this whole thing, that means the solution that we want to apply, or we are taking as a trial or a trial solution, whatever you want to call it, this can be written like this: t to the power r sum over n equals to 0 to infinity a of n t to the power n, right? And since this t of r gets multiplied everywhere, you just need to do this, that is multiply tn with tr. So from n equals to 0 to infinity a of n t to the power r plus n, like this. So this is the kind of solution that we are assuming or anticipating, and as illustrated by our previous attempt, you can see that this is the thing that will work, because if you just see over here, this equation right now will follow a Cauchy-Euler form, a series like this, and writing this solution over here actually comes from this part. So yeah, whatever we did here, we won't be needing them. Rather, we won't be needing only this part over here. That is, whenever you are trying to deal with a differential equation and you want to have a solution near the singular points, we should go for the Cauchy-Euler form. So let's call it CE form in short. So now that we are kind of assuming that this is the kind of solution we want, what will happen next? How do we proceed? Because from the previous example video, you have seen that obviously we need to differentiate this y of t, we need to put it in the differential equation, and then we have to do some dummy index manipulations to get our recurrence relation that will eventually lead us towards some solution. And here we will do the same thing. And also an important fact is that here a0 is not equals to 0. This is important. So what we need to do to find the solution is that I'm just gonna say this out loud, but in the example video I'm gonna show you how this actually works. So this solution, that is this summation over here, marked with this blue color, it needs to get replaced in the differential equation first. That's the first step. And then this series in the differential equation will give us some recurrence relation, and at the same time, when we equate the coefficient of the lowest power of t on the left hand side to 0, we will arrive at a quadratic equation in R, and that is called an indicial equation. And since this R will have a quadratic equation, it will give us two roots. One of them is R1 and one of them is R2. Let's call them like that. And using this informations, we'll see that there are three cases for a solution like this, and we'll explore them with examples. So these are the things that we're going to focus on from our next video, and this will be it for today. and I'll see you guys on the next lecture. Thank you.